Welcome to the Deck Dive, the place we take a stack of sources, tear down complex scientific ideas, and build them back up with surprising context and real insight. Today, we are focusing on the very foundation of our existence, the Earth's crust. It is the thin, solid shell that supports every mountain, ocean, and city, and yet we rarely give it a second thought. Here's the mind-bending fact we need to start with. The Earth's crust, the entire thickness of the rock we interact with, comprises less than 1% of the planet's total volume. Less than 1% of the radius, too. I mean, if the Earth were an apple, the crust would be thinner than the skin. It's almost nothing. Our mission in this deep dive is to understand this incredible thin veneer. We are going beyond the basic definition to explore its dual personality, how it's chemically distinct from the mantle, why some parts are ancient survivors and others are constantly recycled, and how physics dictates why our dry land is dramatically higher than the deep ocean floor. So, to set the stage, let's nail down where the crust sits in the planet's architecture. It is the solid, outermost rock shell, but it is only the top component of a much larger, rigid structure called the lithosphere. This lithosphere is the entire tectonic plate itself. It includes the crust and the rigid, cool, uppermost layer of the mantle right beneath it. This whole structure, broken into plates, is the mechanism through which the Earth regulates its internal temperature. It lets the deep heat escape.
That distinction is absolutely vital because it changes how you view the solid surface of the Earth. Why should you care about this less than 1% fraction of the planet? Because its very existence and stability depend on a delicate balance. The crust, well, it floats on the mantle below it.
Floats. How does solid rock float?
Well, float is maybe a bit simplistic, but it captures the idea. It's possible because of the material science. The underlying upper mantle is primarily made of a rock called peridotite, and peridotite is extremely dense, far denser than anything that forms the crust. This density differential provides the necessary buoyancy for the entire crust and the rest of the lithosphere to sit in a stable configuration. You were talking about a contrast almost like the difference between a dense iron block and a piece of granite floating on a very, very viscous liquid, slow motion floating over millions of years.
That helps us visualize the structure, but how do scientists define the literal line where the crust ends and the mantle begins? It can't be a fuzzy transition, or plate tectonics wouldn't work so predictably, right?
No, it's not fuzzy at all. It's defined by a specific, measurable physical contrast called the Mohorovicic discontinuity.
Right, the MOHO.
The MOHO for short, thankfully. And the MOHO isn't defined by just temperature or pressure. It's defined by a sudden change in how quickly seismic waves, earthquake waves, travel through the rock.
Ah, okay, so waves travel differently through different stuff.
Exactly. When a seismic wave hits the MOHO, its velocity sharply increases. This increase in velocity tells seismologists that the wave has moved from the less dense crustal material into the significantly denser peridotite of the mantle. It's a literal acoustic boundary layer. We know precisely where this layer is because we can detect that change in speed, which provides indisputable evidence of a massive change in rock density and composition deep below our feet.
Okay, let's unpack this in terms of temperature then. If we start drilling down from the surface, which is comfortably cool, how quickly do conditions change? How hot does the crust actually get before we hit that dense peridotite layer, the mantle?
It gets hot, fast. We tend to think of the surface as fixed, but the temperature of the crust increases dramatically with depth.
Right at the MOHO boundary, the rock can reach a massive range, typically 100 degrees C, in areas where the crust is thin and cold, maybe under old ocean basins. Up to 600 degrees C, or 1112 degrees, in areas where there is active volcanism or tectonic stretching. That's hot enough to melt lead easily. This huge thermal stress tells us the crust is not just a passive shell, it's cooking.
Yeah, and what's truly fascinating is the rate of heat increase, the thermal gradient. In the upper crust, that gradient is incredibly rapid. You can see the temperature locally increase by as much as 30 degrees C or 54 degrees for every single kilometer you descend.
30 degrees per kilometer, that's steep. Why so fast near the surface?
Well, it's because the continental crust, in particular, contains higher concentrations of radioactive elements like uranium, thorium, and potassium. These elements decay, and that decay process generates heat right there in the crust itself. It's like having little heaters embedded in the rock. This intense thermal gradient is critical. It drives geothermal activity. It helps create veins of mineral deposits. It's the key energy source for metamorphic processes, literally cooking and transforming the rocks of the lower crust.
So we have this thin, hot layer sitting atop an incredibly dense substrate. That density difference, as you mentioned, is the fundamental physics governing the whole system.
Absolutely. If the crust didn't float, we wouldn't have plate tectonics as we know it. The crust is less dense than the mantle, and this physical reality is why we have mountains and continents. This principle is called isostasy. It basically refers to the state of gravitational equilibrium between the Earth's lithosphere and the mantle beneath it, like balancing blocks.
Isostasy sounds complex, but you're saying it really dictates global geography.
Yeah.
It's the reason why mountains have deep roots, similar to how an iceberg only shows, 10% above the water?
Precisely. Think of isostasy as Archimedes' principle applied on a planetary scale. It explains why a massive slab of continental crust rides significantly higher than a slab of oceanic crust. Both are lighter than the mantle, sure, but because they have different characteristics, specifically thickness and internal density, they achieve radically different states of equilibrium. And that determines whether the surface is dry land or deep ocean.
Right. And here's where we get to the core distinction. Earth doesn't just have one crust, it has two dramatically different types. The thick, ancient continental crust and the thin, constantly recycled oceanic crust. They are a physical and chemical study in contrasts, and they are responsible for pretty much every major geographical feature on the planet. Let's start with the continental crust, the stuff that makes up our land masses. Its profile is one of immense variability and scale.
Yeah, continental crust is thick. It ranges wildly from maybe 25 kilometers up to 70 kilometers, or about 15 to 44 miles thick.
That variability is driven entirely by tectonic history, isn't it? Where continents have crashed together, the crust has wrinkled and stacked up on itself like a rug pushed against a wall.
Exactly. And we see the most extreme examples of that stacking under the planet's largest mountain ranges. Consider the Tibetan Plateau, where the Indian and Eurasian plates have collided. There, the crust has ballooned out to between 50 and 80 kilometers thick.
80 kilometers.
80 kilometers. To put that into perspective, that's roughly the distance from, say, New York City to Trenton, New Jersey. You would have to drive that entire distance down just to penetrate the crust under the Tibetan Plateau. It's a colossal amount of material that has been crumpled and compressed over tens of millions of years.
And compositionally, this stacked material is significantly less dense than the mantle, which is key. It is composed primarily of felsic rocks, that's a geological term for rocks rich in lighter elements like silicon, oxygen, aluminum, and potassium. The most famous example being granite. This low density is the secret to its long-term survival.
Right. And we even have a tight estimate for its overall bulk.
Yeah.
The average density is estimated at about 2.835 grams per cubic centimeter. But, and this is a critical nuance, the density is not uniform. It actually increases significantly as you descend through the crust.
Okay, why does it get denser deeper down?
That density gradient is a key insight. You start around 2.66 GC-meter at the surface, where granites and sedimentary rocks dominate, and it increases to about 3.1 GC-meter at the Moa boundary. Why the increase? Two primary reasons. First, the intense pressure forces minerals into denser, more tightly packed crystal structures, squeezes them. Second, the composition fundamentally changes. While we often call continental crust granitic, the average composition is actually closer to andesite. The upper crust is indeed more felsic, resembling dacite maybe, but the lower crust, which is hotter and under immense pressure, becomes more mafic, richer in magnesium and iron, resembling basalt or gabbro. This lower, denser part of the crust is the transition zone, kind of locking the crust onto the mantle.
Okay, now let's flip the switch and look at the oceanic crust to appreciate the true scale of the contrast. It's like the inverse of everything we just described.
Exactly. The oceanic crust is thin and wonderfully predictable, geologically speaking. It measures only about 5 to 10 kilometers thick, a tiny fraction of the continental crust. This thinness is a consequence of its continuous efficient process of creation at mid-ocean ridges.
And compositionally, it is dense and mafic, rich in magnesium and iron. Its primary rock types are basalt, diabase, and gabbro. It's the dark, heavy stuff.
The fast-moving component of the system, yeah. And we know its internal structure extremely well, thanks to decades of deep-sea drilling and seismic analysis. It forms in 3 specific layers atop the mantle. The uppermost layer is a thin veneer of deep-sea sediments, muds and oozes. Below that are layers 2A and 2B, consisting of pillow lava first, then sheeted dikes underneath. These are basically the solidified plumbing system where magma rose from the ridge, all with a composition of mid-ocean ridge basalt, or MORB.
Like frozen pipes of magma. And the final, deepest layer of the oceanic crust.
That's layer 3, which is composed entirely of gabbro. Gabbro is chemically identical to basalt, but it cooled and crystallized slowly deep underground, forming larger crystals. This whole layered structure is the physical signature of seafloor spreading. You see it everywhere new ocean floor is made.
So if we bring it back to that critical concept of isostasy, what does this huge difference in composition and thickness mean for the planet's geography?
It means everything for geography. The continental crust is thicker and less dense overall. This combination gives it superior buoyancy. Think of two pieces of wood floating in water. A large, thick piece of balsa wood, maybe, that's the continental crust, and then compare it to a small, thin piece of oak, which is the oceanic crust. Even though both float, the balsa wood sits much higher above the waterline because it displaces more volume while having lower density.
That analogy perfectly explains why continents form high ground, often referred to as continental platforms, while the denser, thinner oceanic crust sinks down into equilibrium, forming the abyssal plains, the deep ocean basins that surround our landmasses. The geography of Earth isn't random, it's dictated entirely by the physics of these two floating crust types. Amazing.
It really is. It's elegant physics playing out on a massive scale.
Moving on from the structure, let's dive into the core ingredients. We know the crust is chemically unique from the mantle, but what exactly is this highly refined rock made of? Let's conduct an elemental deep dive into the bulk of the continental crust.
Okay. When we look at the abundance by weight, the results are rather surprising because the vast majority of our crust is made up of just 5 elements, and the top 2 are overwhelmingly dominant.
Number 1, the champion of the crust is oxygen, making up a massive 46.1% of the crust by weight. This is often confusing to non-geologists, but remember, oxygen is the O in SiO2, silica, and the O in almost every major silicate mineral. It's locked in the rocks.
Exactly. It's not atmospheric oxygen we're breathing, it's chemically bonded oxygen atoms in the crystalline structure of the rocks. Following oxygen is silicon at 28.2%. Together, these two elements, the constituents of silica, account for well over 70% of the crust's mass. It's basically a silicate world.
The rest of the major 5 include aluminum at 8.23%, iron at 5.63%, and calcium at 4.15%.
And that's pretty much it. When you factor in sodium, magnesium, potassium, titanium, and all the trace elements, everything else, excluding water totals less than 1%, it's a highly concentrated recipe. This extreme concentration of silicates means the most abundant minerals are, unsurprisingly, the ones built from these elements.
Like what? What are the top minerals?
The most common mineral family by far is the feldspars, making up about 41% of the crust by weight. All sorts of feldspars. Then you have quartz, which is pure silica at 12%, and pyroxenes at 11%. Knowing those 3 groups means you understand the building blocks of most rocks you'll find on Earth's surface.
Now, let's talk about the missing ingredients. What's truly fascinating from a planetary science perspective is not what we have, but what we don't have much of. Specifically, elements classify as siderophile or iron-loving, things like gold and platinum.
Exactly. If you look at the composition of meteorites material representing the primitive composition of the solar system, they are relatively rich in elements like gold, platinum, iridium, and nickel. Yet on Earth's crust, these elements are incredibly rare and highly valued. Why the difference?
It goes back to the early Earth, right? The molten state.
Yes, the explanation is the core of the planet itself. When early Earth was a molten magma ocean, planetary differentiation occurred. Heavy iron sunk to this center to form the core. Because siderophile elements have a chemical affinity for iron, they were effectively scavenged from the surface layers and relocated deeper into the Earth's interior alongside the sinking iron. They went down with the iron.
That is a staggering planetary scale separation process. The crust is, quite literally, the residue left over after the formation of the core siphoned off the iron lovers.
Absolutely. It's chemical refining on a planetary scale.
This depletion explains why gold, for instance, is measured in parts per billion in the crust, requiring intensive mining and concentration processes to be commercially viable. The planet's largest potential gold repository isn't somewhere like Nevada or South Africa. It's the outer core.
That's absolutely right. You'd have a hard time mining it, though. And this leads to another fascinating theory, the late veneer hypothesis. It suggests that the meager supply of these precious metals we do find in the crust actually arrived after core formation was complete, delivered by a final bombardment of asteroids and meteorites after the planet had mostly cooled and solidified its surface. If not for that cosmic late delivery, precious metals will be even rarer.
Wow. So our gold rings are basically alien leftovers.
In a manner of speaking, yes.
Yeah.
Leftovers from the solar system's formation that arrived late.
Okay, beyond the siderophiles, we need to discuss elements that exhibit a quality called incompatibility. This sounds technical, but it's a key insight into how continental crust is chemically refined.
Yeah, incompatible is a useful term. Incompatible elements are those whose atomic size or charge prevents them from easily fitting into the crystal structures of common mantle minerals, particularly olivine and pyroxene, when those minerals crystallize from a magma. Because the mantle minerals reject them, these incompatible elements tend to get concentrated in the remaining liquid melt. When that melt eventually rises towards the surface and cools to form crustal rocks, all those rejected elements are concentrated there.
So the crust acts like the planet's chemical scum layer, collecting all the stuff the mantle didn't want.
Well, scum layer isn't very flattering, but chemically, that's kind of the idea. It's where the misfits end up. The difference in enrichment is striking. The continental crust is massively enriched in these incompatible elements, elements like uranium, thorium, potassium, rare earth elements, by a factor of 50 to 100 times compared to the primitive mantle rock. Oceanic crust is also enriched, but only by a factor of about 10. Continental crust really scoops them up.
And the practical consequence of this enrichment, particularly for uranium, thorium, and potassium, is enormous. It means the continental crust generates its own heat internally through radioactive decay.
Exactly, which connects back to what we said earlier.
This internal heat generation is what contributes to that steep thermal gradient we discussed, making the continental crust less thermally stable perhaps, but also providing the energy for long-term processes like metamorphism and helping maintain its buoyancy by keeping it warm and slightly less rigid. The oceanic crust, lacking this level of radioactive enrichment, is much colder and denser overall.
Correct. And finally, just a footnote on rarity. Two other elements, tellurium and selenium, are also scarce in the crust, but probably not because of the core. They were likely depleted because they formed highly volatile hydrides compounds with hydrogen. These would have escaped early in Earth's history as gases, potentially lost to space before the crust fully solidified and the atmosphere became more stable.
Okay, so we have detailed this highly refined, chemically unique shell, but how did it get here? Now we jump into the timeline, tracing the incredible, violent evolution of the crust from a molten planetary state to the stable landscape we have today.
Yeah, this is where the story gets really dynamic.
We have to begin at the very beginning, 4.6 billion years ago. The Earth formed through accretion planetesimals, basically small protoplanets colliding and sticking together. The energy released by these catastrophic collisions was so immense that early Earth melted completely, becoming a massive planetary magma ocean, just a ball of molten rock.
Hard to even imagine. And as that incredible heat dissipated and the planet began to cool, a skin formed on this magma ocean, its first attempt at a crust. We call it the primary or primordial crust. However, this crust, likely basaltic in composition, was destined for failure.
Why failure?
It faced continuous destruction. Imagine large, late-stage impacts from leftover debris that would reliquefy massive segments of the surface. Combine that with fierce early erosion, maybe a denser atmosphere, and the initial chaotic stages of plate tectonic activity starting up. The critical detail for you to remember is that none of Earth's primary crust survives today. It was all destroyed, melted, and recycled back into the mantle during the Hadean Eon, the planet's first half-billion years.
So total reset. Once that initial phase of extreme violence subsided, the planet settled into a more constant, predictable cycle of creation and destruction. This led to what we call the secondary crust, which is essentially equivalent to the modern oceanic crust.
That's right. This secondary crust is constantly forming today at mid-ocean spreading centers. Here, the underlying mantle experiences partial melting. This melt, being basaltic magma, rises to fill the gap created by the separating plates, creating brand new ocean floor. This process is highly efficient and is a primary driver of plate movement, often referred to as ridge push. It literally pushes the plates apart.
But Earth is a closed system, more or less. If we constantly create new oceanic crust at these ridges,
we must destroy old crust at an equal rate somewhere else. Balance the budget.
Right. And that destruction happens at subduction zones.
Exactly. These are deep ocean trenches where the denser, colder, older ocean plate sinks back down into the hot mantle below. As it sinks, it heats up, releases water, melts, hydrates the overlying mantle wedge, and its material is eventually recycled back into the deeper mantle.
It's a planetary recycling program.
A very efficient one. This constant, efficient recycling process imposes a strict age limit on the oceanic crust. Because it is continuously consumed at subduction zones, the oldest oceanic crust we can find on the seafloor today is only about 200 million years old. To a geologist, that is shockingly young, just a small chapter in Earth's 4.6 billion year history. Dinosaurs walked on crust older than the oldest seafloor we have now.
Okay, so that's the young, fast-moving oceanic crust. Now we transition to the true survivor, the tertiary crust, which is the continental crust. This material acts as the planet's geological record keeper because it is designed to last.
And the age difference is just staggering. While the oldest seafloor is 200 million years, the oldest continental crustal rocks are preserved in ancient, incredibly stable regions called cratons. We find these stable cores or shields all over the world, like the Acasta gneiss in Canada or the Narrier gneiss terrane in Western Australia.
And how old are these rocks?
These rocks date back between 3.7 and 4.28 billion years. Think about that. This is material that existed when there was likely little to no free oxygen in the atmosphere, and life was just maybe single cells barely getting started.
That's incredible, almost back to the beginning.
Almost. And researchers analyzing tiny, extremely resistant crystals of the mineral zircon within the Narrier gneiss terrane have pushed the absolute age record even further. They've found individual zircon grains as old as 4.3 billion years. That means those tiny crystals crystallized when the planet was just 300 million years old. They are the closest thing we have to a physical relic of the Hadean Eon, like tiny time capsules.
And even if we set aside those record-breaking fragments, the estimated average age of the entire current continental crust is still profoundly old, about 2.0 billion years. It's the permanent, enduring component of Earth's surface.
So this raises the single most important question, really. Why? Why does the continental crust survive for billions of years while the oceanic crust is destroyed every couple 100 million years? What is the mechanism of survival?
It must come down to how it's made and its properties, right? That buoyancy again.
Exactly. The survival mechanism is twofold: how it's made and its inherent buoyancy. Continental crust is formed primarily at subduction zones, but not directly from the sinking plate melting entirely. Instead, the subducting oceanic crust releases water into the mantle wedge above it. Water acts like a flux, lowers the melting point. Precisely. That water lowers the melting point of the mantle rock, causing it to undergo what geologists call flux melting. This generates magma that is chemically different from the sinking basalt. It's always a step removed. Then, through a process called fractional crystallization, as this magma rises and cools, minerals crystallize out in sequence. The remaining melt becomes progressively enriched in lighter felsic components. It's effectively taking dense basaltic material and chemically refining it into lighter, granite-like material. This is why arc volcanoes, like those ringing the Pacific in the Ring of Fire, often erupt andesitic or dacitic material, which are the building blocks of continents.
So continental crust is chemically optimized to be light and buoyant from the very start. And once it forms, it resists recycling entirely.
Exactly. The key to preservation lies in those ancient cratons we mentioned. Most crustal rocks formed before 2.5 billion years ago are located in these cratons, and they possess what geologists call deep, cold lithospheric roots. This isn't just the crust, it's the mantle part of the plate underneath it too.
Ah, so the whole plate under the craton is special.
Yes, this old continental crust, and crucially, the lithospheric mantle root right beneath it, are together less dense and much more rigid than the mantle elsewhere. Because they are less dense overall, they are incredibly buoyant and thick-acting, like giant, permanent, unsinkable rafts anchored deep in the mantle, maybe hundreds of kilometers deep.
Okay, so that's the definitive answer to the survival question. These photonic blocks simply float too high and are too light and stable to be forced down into the subduction zones. They resist being destroyed by the very process that helps create new continental material, allowing them to endure for eons.
That's the core idea. They are survivors by their very nature.
And we can clearly link the formation and consolidation of this buoyant tertiary crust to the great geological cycles of the Earth. The creation of new continental mass seems to coincide with periods of intense orogeny, which is the technical term for the process of mountain building.
Absolutely. These major mountain building events are tied to the assembly of supercontinents like Rodinia, Pangaea, and Gondwana throughout Earth's history. When these continents collide, they generate huge amounts of heat and pressure. They stack the crust up incredibly thick, like in the Himalayas today. And these collisions often trigger massive pulses of magma generation, derived from that flux melting process, which contribute to new, stable crustal volume that gets added to the edges of the cratons. The formation and preservation of continents are synchronized with the rhythmic breathing of the planet's tectonic engine, the supercratonid cycle.
And the consequences of this entire dynamic system, the constant formation, destruction, and movement of these plates governed by density and heat, is what we experience daily, sometimes dramatically. Movement within the continental crust manifests as powerful earthquakes on land, and movement on the seabed, especially at subduction zones, creates the terrifying forces behind tsunamis or tidal waves. It's all a consequence of the planet trying to release its internal heat through this thin, dynamic shell.
Yeah, it's the planet staying active, shedding heat.
So let's wrap up this deep dive by just reviewing the sheer scale and importance of what we've discussed. The Earth's habitable life support system is housed in a shell that constitutes less than 1% of its volume. Yet this shell is chemically refined to hold a stunning 46% oxygen and 28% silicon by weight, the key ingredients for rocks and, indirectly, life.
And we have seen the dramatic dual nature of this planetary skin. There's the thin, dense, young oceanic crust constantly being recycled every 200 million years or so, serving as the raw material generator. And then we have the thick, buoyant, ancient continental crust, the eternal survivor, which preserves rocks dating back as far as 4.3 billion years. And it dictates the geography of our planet through its stubborn resistance to sinking.
This constant, vast planetary cycle driven by internal heat, the creation and destruction of crust, is only possible because the continental crust found a mechanism to survive.
Which leads to a final provocative thought for you to mull over. Consider this. If the process of fractional crystallization at subduction zones had been slightly less efficient, meaning the early continental cratons and their underlying lithospheric mantle roots had formed just a little bit denser and therefore slightly less buoyant, what would the visible surface of Earth look like today? Would the world be entirely covered by a single global ocean, with no significant land masses ever surviving above sea level? Would complex land life even have evolved? Something to think about.